that does this by hash. So I take all of the bytes of the function, I strip out pointers, and then I do a one-way hash function, and I can publish a table of those hashes with my reverse engineering tool. And then if any of the functions that you have exist within that database, it can recognize them. Unfortunately, this doesn't work if you're analyzing something new or something made with a compiler that you don't have access to. And the latter was my case. This software was written with a compiler that I don't yet have symbol importing working for. So another trick that you can do is to recognize it by port. And doing this is looking for the global address of a port that you know interesting code uses. So for example, there's a serial port, and there is an address that you write a byte to have that byte come out the serial port. So all you have to do is look for that address, and you get all of the functions that write serial traffic. The same for reading. So you can do a select statement in SQL, and you can get just a list of the functions that write out to the serial port. And usually there's one or two of them, and they're both put byte. Now, the loader itself is one of two halves of the, it's composed of two halves. So when you first power this device up, it quickly makes sure that all of the ports are correctly initialized. Because if you have, say, an input and an output next to one another, or you accidentally have a port and output mode when it should be input mode, you can tie up a bus. And if you don't configure the I2C bus properly, then you break it for everybody, and then the USB to serial chip can't function. So if you were to just write a simple blink the LED firmware image and place it within this chip, the board would cease to function on the USB port. Following this, there's a main loop, which accepts the update and eventually jumps to the entry point of the lower firmware. And because it configures all of the I/O and the clocks and the interrupts and everything that we need to have the device working, it makes sense to keep the bootloader at the top and just link it into our own custom firmware. So this is an example of the code that actually initializes a port. And the P3 cell, P3 out, P3 dir, they select which function the port 3 will be used for, which direction it will be used, as well as what its output values are. So the bis.b, bit immediate set byte-wise. So it sets the 16-bit of port 3 high. Rather than reverse engineering all of this code and marking out exactly which port should be set high, which should be low, it's easier to just copy everything over and link in elsewhere. So you don't have to convert from this to the equivalent C, and then from C to identifying it on the schematic, and then from the schematic to the intent that the programmer had. You can do SQL queries to identify these, though. So this selects all assembly code where an address less than 100 or less than 200 is used. This gives you every access to every port, and then you have a table on which you can compare the ports. And the interrupt proxying is performed by handler functions. So, for example, the DMA access interrupt occurs at 0xFFE0. So at that address, there is a 16-bit word that is the address in memory that execution should flow to when the interrupt fires. And the handler is at FB78. This could be anywhere within the upper region. But it branches to the contents of F70. So for almost every interrupt, there's only one exception, it just takes the address that everything should be at, and it subtracts a couple hex from it. So FFE0 becomes F7E0. FFE2 becomes F7E2. So if the native address is in the FFE0 to FFFF range, the proxied address will be in the F7E0 range. And on the red version of the firmware, this region is actually slightly lower because it has a more complicated bootloader. But the infuriating thing about this, and what took me a week to notice, was that the reset vector is not among those that is proxied. And while flash memory begins at 2500 hex, this is where the chip begins to execute after it exits the bootloader. The interrupt vector table entry for the reset vector is ignored, and instead execution jumps to 2502 hex. The first word of flash memory is always left empty, and execution always begins on the second word of flash memory on this firmware image and only this firmware image. If you look at any other image from any other compiler, execution will begin at the very bottom of flash memory. So at this point, we know that the loader stage exists from F800 to 10,000 hex, that it proxies the interrupt vector table, but it doesn't itself use interrupts. So it can't have any event-based programming. It can only sit within a tight loop. And we know that it configures the ports and the clocks properly so that the chip can function and the bootloader can speak to the PC. We also know that the application stage is supposed to go from 2502 hex to F7FF, and that the interrupt vector table is supposed to begin at F70. So we can write a new GCC target. And in GCC, there's a linker script, or a .x file. There's one per family member, so you link differently for each chip in the series. And this is done because different chips have different amounts of memory and they begin at different places. You might want a firmware image to exist for a chip that doesn't exist. Because you might want to compile a single image that will work on multiple MSP430s and not care which chip is sourced during manufacturing. So taking advantage of this feature, I moved the text region, which is where executable code exists, from 2500 to 2502, and then I reduced its length so that it no longer collides with the end of memory. The data region is RAM, and I left that unchanged. Then the vectors I moved down to F70. And the bootloader and info memory and such are ignored by the compiler. I also had to crop the bootloader out. The nice thing about the Intel hex format is that each line is actually readable text. It contains a length, a starting address, and then the data. And you can just crop out the lines that you don't like. So a quick Perl script can say, give me this firmware image, but only in this memory range. So I cropped it out. You'll note that there's still some blue lower in the image, and that's because blue doesn't refer to data that's actually in the image, but data that's referred to in the image. So the blue band beneath the interrupt vector table is a region of memory pointed to by the proxied IVT. Then you compose a makefile, and in the makefile you specify which CPU and which linker script with the -t argument. Then you copy it to an Intel hex file. You crop off the last line of the bootloader. So then you can use the cat function to concatenate the two together, and that gives you a single firmware image that you can write to the chip that contains both Texas Instruments bootloader and your application software. So then, as it stands, I've brought this to Hello World. You can compile an image, you can write it onto an EZ430, and it runs. But I haven't made any utility out of that. So the next step would be either to build something out of this, to make, say, an I2C SPI adapter, like the Bus Pirate. If you look at the Bus Pirate, it's from Hackaday. It's a PIC microcontroller and a serial adapter. And then the PIC microcontroller does bit banging on any protocol that you specify over some GPIO pins. Well, this could do the same thing because it exposes its GPIO pins. It also exposes line-level serial if you need to do fast communications with, say, a Zigbee radio. This is also useful for side-channel timing attacks, as I did in my first lecture of this Congress. So you can write a program that runs on the EZ430 and has immediate access to the hardware pins. It has no latency. It's the same as the old parallel port bit flipping stuff, except that we don't have parallel ports anymore, and they were never that good to begin with. The other thing you can do is reverse engineer the actual JTAG standard for the MSP430. Because while they've published enough to tell you how to program a chip, the documentation hasn't been updated in quite a while, and it doesn't specify how to program the new 20-bit chips, the MSP430X. So you could modify this device to, say, spit out debugging information, to do things like that. And you can add support for proper JTAG, whereas it only supports SPI-by-wire, the 2-wire JTAG standard. This is a commercial I2C adapter called the Aardvark from Total Phase, and this is the one that I used to dump the I2C EEPROM from the EZ430. You could easily make a compatible product to this, and you could do it with a device that you can buy for $20 US. In the timing attacks, you send serial traffic with the start bit early, and then you can actually watch how long a password comparison takes within a victim chip. So for about half of the MSP430s, by doing this, you can figure out how correct a password guess is in like how many bytes out of your guess are correct. But to do this, you need absolutely low latency. If there's a context switch caused by the preemptive multitasking of your PC, then PC software that's trying to bitbang this will fail. On a microcontroller, you have no such interferences. You can write an application that runs on the board and behaves exactly as you instruct it with no operating system to get in the way. This is the second generation of the password cracker. As for reverse engineering JTAG, the documentation tells you how to program it, but it doesn't tell you how to debug it. You can't, by the documentation, single-step the chip or set a breakpoint or do any of those things that are necessary in a proper debugger, even though the hardware supports it, even though TI's tools support it. So your only option is to use the closed source tools, a closed source proxy for GDB and such, or you can reverse engineer it. There's work in progress to break this that I'm not the primary author on, but I can refer you to it if you're interested. This is the recording that I took of JTAG. And we have a tool now that the guy who's doing the JTAG reversing authored, which can actually parse this. So you can spit out from this recording a list of read and write commands to memory. Soon breakpoints will be supported as well. What would also help would be able to identify this within the code. So instead of looking at the line-level recordings and writing tools to identify them and such, you could identify the JTAG I/O functions which are within the TI implementation of this. So there's instruction shift, data shift, set TCLK and clear it, and that sort of stuff. There aren't many functions that act as the primitives for this sort of stuff. So if they can be identified within the firmware image, you could write a script for the reverse engineering tool that runs through and identifies, say, every instruction that might be shifted in. And then you've got a list that you can check off in your recordings. So if you know that, say, 37 instructions exist, then if you found 35 of them, you know that 2 remain and you know which 2 remain. So are there any questions? Yes?
How did you get the sniffing over the JTAG? You just connected to some kind of probe or something, and
yes. So this recording is from an FPGA that has been reflashed with a bitstream to make it behave as a logic analyzer. And then the software that you see connects to it through a serial port. When you push a button, it does a quick recording at up to 100 megahertz. And then the recording gives you the logical value of each pin at each moment in time. This is also available in a text file that can be parsed by script.
So, and can you buy this on